guys to know this how to do the superposition. And the assumption for doing superposition is that the material is elastic, the deformation is a small deformation. Small deformation means that if you apply one set of loads, so the results will not affect the results when you apply another set of loads. So this is small deformation, elasticity. So if these two assumptions are holding true, and so you superposition will work very, very well. And then we talk about the street energy. Street energy is very, very important one, because we are going to talk about another theorem. The street energy, we talk about the street energy. And if we apply a load for the tensile, and it's axial loading, either tensile or compression, and how to calculate the street energy, right? Is a street energy. So this F is the force. So this is the street energy is related to the geometry of your specimen and also the material of your specimen. This is energy, total thing. And for torsional, we have these two equations. One is for the cross-sectional area that is uniform throughout the length. So this one is more general, and this is what I told you guys. For tension, for torsion, we have different equations. And for direct shear, and the direct shear is the case that when you shear using force, and to shear, this is a structure. So this is called direct shear. And why the direct shear here, it is singled out? Because we have another shear. Another shear is called the transverse shear. Okay? You guys know that last time I told you what's the difference between the transverse shear and the direct shear. And transverse shear means that, because say this is my beam, right? If I have a load, if you apply load, not this load, not just have bending moment, but also this guy is going to generate the shear along this cross-sectional area. What do we call this shear? It's called transverse shear. Right? So also please note that if the structure is a slender beam, a slender structure, the transverse shear can be ignored. Can I write down, guys? If the beam or the structure is a slender one, you know, that's thin, very thin. This is a very skinny, very thin structure. The transverse shear can be ignored. Okay? Question?
What's the difference between transverse shear and the normal shear?
The transverse shear is when you apply a concentrated force. So this guy generates the load, bending moment. Yeah. And at the same time, along this is the point of when you apply the load, where you apply load, and that's the cross-sectional area, you will have transverse shear.
So then a normal would be like going at the end of the line.
Direct shear means that for this is my structure, I have a force that shear it. So that is the direct shear, or it's a normal shear. And usually we call direct shear or normal shear. Not called normal shear, we call it direct shear. Okay? So these are transverse shear. Transverse shear, let me draw this one. A transverse shear means that this is my beam. If I have a force, not just this concentrated force, can be a uniformly distributed force. Along this cross-sectional area, I have a V. So this V is called the transverse shear. However, if this beam is a slender beam, and this transverse shear can be ignored. That can be ignored means that it will not affect your results, but still you lose some accuracy. Okay, so for research purpose, you need to consider all these things. But for practical purpose, if this beam is very, very slender, and you just ignore it, just for because we are lazy, right? Research people are lazy. You can see. So this is the transverse shear, and they are related to the geometry, the shape of your cross-sectional area. So this sheet covers all the equations: tension, torsion, bending, Derivative shear, transverse shear, and usually we don't have the derivative shear directly, okay? So for some special case, for some very simple case, we have this one. We usually have 1, 2, 3, 4. And also if the beam is a cylinder, and you just cross it out and only think about these three. These are three, the dominant, this is the case, the dominant, the loading conditions. So then we talk about Castigliano theorem. So have you ever heard of this Castigliano theorem? No? Who have heard of? Raise your hands. Nobody heard, okay. Nobody heard Castigliano theorem. It is an energy method, the energy method to solve the structural problem. The difference between energy method and the partial differential equation method is that, so we look at this energy, okay, for the whole system. And the underlying assumption is that the structure system, it reaches the state of equilibrium when the energy of the whole system reaches the minimum. Okay? One more time, the energy method, there's a lot of energy methods. Castigliano method is just one example. There's a lot of energy methods. Energy methods approach the structure system. Approach the system by looking at the total energy of the system and make sure so this system reaches the state of equilibrium when the energy reaches the minimum. This is not just a structure for all the systems in the universe. If we say this system reaches a state of equilibrium, it means that the energy of the whole system is the minimum. Otherwise, it is not the state of equilibrium. So, by this means, the differential equation methods approaches are totally equivalent to energy method. So I taught a lot because you do not have this background. So it is categorized as energy method. So we can see what this Castigliano theorem says. It says that this U, okay? The U is the straight energy for the whole system. The whole system, not just a single part of the system. It's a whole system. If you know apply a force on the system Fi, okay? Fi, and then the deflection because of this force can be calculated using this equation. It means that we take the derivative of U, the straight energy of the whole system, with respect to this is the applied force, we can get this guy's deflection, corresponding deflection. All right? So you need to know that is delta I and Fi, and you must be talking about the same point in the same direction. Can you write down, guys? Same point, same direction. And because the force usually have three directions: F1, F2, F3, and correspondingly, you should have delta 1, delta 2, delta 3. That means the displacement in three different directions. All right? Be very careful. So this is one case. The second case is just a variation. Variation is that this is a force. Now I'm talking about moment. And this moment can be bending moment, can be twisting moment. Can you write down, guys? The torque is a twisting moment. I need to tell you, torque is a twisting moment. Moment can be bending moment or the twisting moment. So this one says that if I have a bending moment, so this theta I is the slope, okay, slope of the beam. If this mi is a twisting moment, and theta I is angle of twisting, that's the corresponding. So this equation takes the derivative of strain energy with respect to corresponding either bending moment or the twisting moment, and you will get this is either the slope of the beam or the twisting angle of the beam. Questions? Now, if we want to use this one to solve the problem, and we can see the how we approach this problem. First, not calculate. express the string underneath. Okay, we call this the string underneath. Express the string underneath of the whole system and in terms of I. And then we just take the derivative. What? Some students might be asking, and this is kind of very confusing. If I apply a load, I can get this delta I. What if I don't have actual load? Can I still use this equation to get the corresponding either deflection or this is the angle using this equation? The answer is yes. Okay. If you do not have an actual force or the moment, you can still use either of these two equations to get the displacement or the theta. How to do that? You can just assume you have a load zero. But finally, after you take the derivative, you just force this is the force or this is moment to be zero. Then you get this delta I from sigma. Okay? So this is what I want to tell you. You know we will have examples in the stream. You can see this is what I say. If this is the caustic Liano's method can be used to find the deflection at the point, even if there is no force applied at the point. That's what I said. Okay. So apply what we call the fictitious force. So this is just imaginary force there at that point, and in that direction of the desired deflection, and set out the equation for total string underneath, including the underneath due to Q. Okay, just assume this guy is zero, but finally we know this guy equals zero. And then take the derivative and just force Q equals zero, and you will get this corresponding delta. So make sure. So this fictitious force Q must be in the same direction of the flexion you are interested in. Bobby.
If there's no force at that point, why would it still have any like deflection? Like, wouldn't it just have no deflection if there's no force on that?
Yeah, you can see if this one, if I find it here, there is no force.
Oh,
I know I know this is still deflect.
Right? No direct force,
Yes.
But there's still a force somewhere out there.
Yeah.
Okay.
Because we have the force or moment on other points, on the neighboring points. That's a good question. Because the structure is continuum, right? If you apply deflects one point, definitely the neighboring points will be deflect accordingly. So then we need to find out this is the deflection without finding underneath. How to do without finding underneath? But this is the du. Okay, so this is the for cases requiring integration of string underneath, it is more efficient to obtain the deflection directly without explicitly finding the string underneath. How to do that? We just do some math with this manipulation. The partial derivative is moved inside the integral. Right? So here delta I equals du dfi. So this is for bending moment. If I have only for bending, this is the string underneath. So what is inside this parentheses is my string underneath u. Right? I just write it here. However, I know that based on the knowledge I learned from the calculus, I know derivative and integration, and I can change the order. You guys agree? I change the order of the integration and the derivative. I will not change the result. You guys agree? Okay, so I just do it. You can see, I just put this derivative inside this integration sign. So this is my m square, and you need to know that I'm taking the derivative of the whole thing with respect to fi, not m. That's the result. This is for this one. I just here is a square, and the square goes down as a factor. M. This is copy m here. Then I just multiply by the derivative of m with respect to fi. Are you guys okay? And then this is the denominator. I still copy the 2ei. Now, if I just cancel these two, so this ei, I just rearrange this one. So this is my actually, this is to the, you have U, okay? I'm sorry, this should have U here. Delta I equals this. You can see I did not explicitly show the U, but I show the M. You understand? You guys have any questions regarding this one? So this for only we only have bending moment. Any questions? Can somebody help me look close the door? I don't want this to other people. Okay. So this can simplify the math. It's very helpful with the fictitious for Q, since it can be set 0 after the derivative is taken. Questions? No questions? No questions. For other cases, and for the torsion and tensile and the compression, we can use one equation. We use this one. Let me write down. And we are going to use. So this is the bending. And so this is the XO. We call this XO. And so it equals this is 1 over AE. This I is the central force, which is the axial force on DI on DI. Yes. And so this the torsion. For the torsion, we have this theta I. And theta I is the twisting angle, torsion twisting angle. It is 1 over Tj, and T is the twisting moment, and dt and dm is mi. Also here we have dx, and so this is for the bending. We have bending here, bending axial torsion. So we are going to use this equation for our example. Now here is one example here. So we have the two steps. So this one, this one, and the geometry is given. The total is length, half length for this size and half length for this size, and we have the concentrated force at the left end. Now, we are asked to use Castigliano theorem and to determine the deflection of point A, okay? Deflection of point A and point B. Point B is a connection or connecting point between this one and this one. So due to the point F, we have F here, and the second area moment of sections A and B are I1 and I2. I1 and I2. So you can see from these three equations, the delta is dependent upon not just only your material properties, but also the geometry. Right? Now, we want to solve this problem. And how to solve this problem, guys? So this is F, and this is the F for the force, and this is the point A. And how to solve the problem? How to solve the problem? So I know that this delta I equals du and dfi. So this is the equation I have. But for this one, what I need to do is that from this concentrated force, how can I calculate the stream energy U? Right? How can I calculate the stream energy U? And in order to calculate the stream energy U, we need to analyze that. And for these three cases, 1, 2, 3. When we apply this series here, and which one we have? We do not have torsional, right? We do not have torsional. we do not have axle. Agree? However, we have a bending because here's if you pull it down, so this whole beam will be bent over. Agree? So the bending moment here is not a constant. It is related to the distance from which the distance between the point of interest to the point A where you apply the F. So I can see so for any point, let's see for the three-point diagram here. So this is O, okay? So this is X. So here is half L. So this is a half L. So there is another half L. Is another half L. Now, for any point X here, right? For any point X, I know sigma mx equals 0. You agree? Because I know this guy is in a state of equilibrium, right? Are you confused? Okay, so at this point, this X, right? So this is without loss of generality, I just use this one as a generic point X. For this X, sigma mx, actually it is moment. If this is X and this is Y, if X and Y, we will say, so this is a sigma, I will not write this is sigma mz along Z, right? Along Z direction and at the point X. So this one must be equal to 0. Okay? Okay, if this is the case, this is the M, okay, so this, I just draw up here. So this is, I have a bending, this is F. So this is X. So I have this, you bend it here. And then there must be a MZ, okay? So this MZ here, and this MZ must balance your F. That means so this one equals 0 means we can get MZ, which still use that convention. If we cause this guy to rotate counterclockwise, is a positive. That means F multiplied by X equals minus MZ equals 0. Right? Are you guys okay? And then I can get this is the MZ equals F multiplied by X. You agree? Okay. So M equals Fx. So Fx, I'm just put this minus sign here. I just I use this one is mz. So this is Fx. So this mz equals Fx, and then we can get using that equation delta I. So this is the delta I, delta A, okay? Delta A equals du and df. So we can get that equation. So this equals from this equation here for first one, guys, you can see the delta I equals 1 over EI is M, then dm and df dx. You guys agree? You guys agree, guys? Okay. I also know that for this kind, this half is I1, this half is I2. So this half is I1, so this is I2, I2 equals 2I1. So I need to differentiate as these two halves. As we can see from 0 to half L, and to half L, we have is 1 over EI1 and EX, and then plus 1/2 RL to L. So this is EI2 EX. Are you guys okay? And then this is M. You can just plug in M equals Fx. M equals Fx. You can see. This is M equals F multiplied by X. And then you will know dm and dx equals df, I'm sorry. df equals X. And you can just plug in. And you will have here from 0 to half L, 1 over EI1. So this is M is Fx, df, X, another X, and dx. And then plus here, half L, now this is 2 EI1. So here is M is the same thing, same Fx multiplied by another X and dx. Questions so far? Now you can just do the integration. This is X from 0 to 2 half L. But here this X is from half L to L. And EI1. So now you only have one I1 here. You can just finish this following step. Okay.
Is that gonna give us the total deflection, or like is that gonna give us the deflection at a specific point?
This is the deflection at a specific point. So this says that the deflection at the specific point. Right?
Okay, so we're solving for the deflection at A. Like that's what that equation is.
Yeah. So we take the derivative of the total energy with respect to the force at that is acting on the point of interest. So this delta I and Fi, they must be referring to the same point and must be referring to the same direction. What? Questions? No question? No question? And we going to move on. Next one, I'm going to ask you to finish it. For next one, for the point B. And for point B. For point B, we do not have this is the concentrated force at the point B. What should we do? And we will apply a fictitious the force Q here, right? And fictitious we use dotted line and to denote it. That means this imaginary, it is not actually there. So however, when we do the free body diagram, so here is my, this is the F, and here is my Q, right? When I do the free body diagram, guys, I need to take care of this, the Q. Whenever you see a concentrated force, and you always use this point where this is concentrated force is applied as a demarcation line, and you need to differentiate these two intervals. And how to do that? From 0, this is half L. So this is another half L. So this is origin. So this is X. So this is Y. Right? So for X is less than half L and greater than 0. For this interval, okay, for this interval, I have the same thing. I have this free body diagram, and so I have this MC. So this is my F, This is my x. So this guy reaches the state of equilibrium, right? And so that means mz equals fx. For this one, I still use that equation. F is a sigma mz at x point equals 0, and then we have fx minus mz equals 0. So mz equals fx. However, for another interval, this is from half L and 2L, and we have a fictitious Q here. So fictitious Q, if we draw the free body diagram again, so here is my Q, right? So this is my Q. So this is my X point, and which is larger than half L. So here is half L. So here, I'm interested here. So this is my MZX. Now this time, so the MZX. So here is this is the F, right? So this is F. So here is a Q. MZX equals F, right? F multiplied by the total X. Agree? Then, in addition to this, I have a fictitious Q, and then plus Q. Now, this time, this guy's effective arm equals X minus half L. So this is my X. And then you can just have, this is delta B equals the two different equations, two different interval from I1, okay? So here is for the first interval, left half, 1/2 L. And so we have put this fx here, see, you still use that equation, use this equation. And we have fx multiplied by dm df equals x, and then dx. So this on the left half. Well, for the second half, be very, very careful. It's 1 over e I1. So because I2 equals 2I1. I2 equals 2I1. So from half L and 2L, yeah? And so you need to use this M. And so we will have first M, dm, right? And dm. So we write this M here. So this M equals fx plus q xl n minus l. So this is the M. And then dm and df and dm for here dq, right? dm dq. dm for this is dm and dq. So here is a dm dq also. I'm sorry, guys. So this is I. So here is fx m. Okay, m. So then here this one is dm dq. So dm, you know dm dq. See, dmz and dq equals 0 because it does not have q, right? So this one and dmz and dq equals x minus half L, right? So you can for here I just plug in. So this one go here, and this one go here. So you will have this is a dx. So because dm dq equals 0, this guy equals 0, and then this integrand equals 0, so this equals 0. Right? So finally, I will have so this is finally is delta b equals this part. For this part, I'm also q equals 0. So this equals 0, but I have fx. Here dm dq equals this, and so we will have, let me write this down. And 2ei1 half l. So for this case, we have f x q equals 0. Just get rid of it. This one equals x minus half l, and then dx. So I want you guys to finish. Take a photo, and then I post this one on the cameras. Let's do the integration. Okay. Okay, so you can take a look at this one. Any questions regarding this Castigliano theorem? It is very, very beautiful, very, very the powerful tool for us. No question? No question? Let's move on to the next one. Next one is the deflection of curved beam. Previously, we have learned the stress of the curved beam, but this is now we call about deflection of curved beam. The reason so this topic is so important is that in our daily life, when we design something, the curved the members, curved beam, they are commonly seen in the structures. We have to be very, very careful. So here, I will talk about the stake, the curved beam. So slender curved beam, that's another story. It is for the stake curved beam, you can see we have several the sphere analysis. So for the first one, due to the bending moment, right? For this one, if we just call it, because the bending moment, we have axial force F theta. So suppose we have F, this is a concentrated force. So this is a concentrated force for any generic, this is theta angle. This is theta and this is d theta. For any generic theta angle at this point, because of this guy, and we will have the bending moment resultant from this F, which equals F multiplied by the effective the arm of this F from this point, and which this F multiplied by the distance from here and to here, and which equals the R multiplied by the sine theta. So bending moment, because of bending moment, it is a bending moment. And the axial force on this one, axial force on this theta, F theta, okay? So this is F and this F theta. The bending moment due to F theta, because this F theta, right? This F theta, it has another bending moment. The things, the neutral axis and the centroidal axis do not coincide. You can understand this one, do you? Because for the curve, the curved member, the neutral axis, no matter how regular your cross-section area is, the neutral axis and the centroidal axis, they are different. Do you guys agree? How different? It depends upon the curvature of this is the curved beam. So if I have the theta, I have theta here. Right? So this F theta is decomposed from this F. I know that because the neutral axis and centroidal axis, they are different. So if you have F theta, and you will have another bending moment because of this guy. So lastly, at the transverse shear FR, see? FR, it is parallel to the surface but perpendicular to this normal direction. Questions regarding this? So all these three guys, all of these, they are resulting from this earth, from this concentrated force. Okay, so string energy and due to the bending moment, so this is a bending moment. We have a bending moment, okay, bending moment. The m squared d theta and 2ae. So this is stress that is based upon what we have learned in the stress. And so this E equals the difference between this R, the center R, okay, center R minus Rn. Rn is the radius of neutral axis. The Rn is the radius of neutral axis. So this is for the bending moment. And then for the axial force, the string energy because axial force is also this F theta. Okay, F theta is also generate a bending moment, and also we use the equation. And this is equation from the F theta to calculate the U2, that is contribution from the F theta. And then due to the bending moment due to F theta, okay, bending moment. Sorry guys, this one is axial force. This axial force, we just move this axial force to neutral axis. So this is the bending moment due to the F theta. We have this U3. And then the transverse shear FR, and we use this. You can see, let's go through this one. First one is because the bending moment, and we have from this F, it equals F multiplied by the distance and from this F to the point of interest. So this is from the bending moment. And second one is axial force. And we just assume this axial force here is applied and to the neutral axis. As a result, we have here. However, actually, it's not the case because the centroidal axis and the neutral axis, they are different. And so we have this bending moment. And I will say the AE. So lastly, the transverse shear. And we have, because the transverse shear force FR, we have this component for the string energy. So that means the total string energy equals the summation of all these three guys, all these four guys. Right, guys? You guys agree? So why here this one is negative? Why this one is negative? Okay, and I will tell you, this one is a bending, okay? Bending, this M tends to rotate this point the counterclockwise, right? However, this F theta, and this F theta, we just assume this F theta is moved to this centroidal axis. The centroidal axis and the neutral axis, they have a difference. That's the difference is E. Usually for this case, we have neutral axis first, and then centroidal axis, and from this is the center. That's the reason. So the contribution of F theta is going to bend this point clockwise. That's the reason we have a minus sign here. You have sense, guys? Are you following me, guys? So here, This is my centroidal axis, right? And so usually my neutral axis is here. My neutral axis here. This